Want to kick us off?
For sure. Hello, everyone, and welcome to our presentation on Trillium Hyperloop's state-of-the-art software system and our design for the Flywheel test system. My name is Bruce Gillespie, and I'm the linear induction motor lead at Trillium Hyperloop. Now, Trillium Hyperloop is Western University's Hyperloop design team, and we are also their newest engineering team. We started in April 2020 when a group of engineering students who were passionate about sustainable transportation read the Hyperloop Alpha paper and wanted to work towards competing at a student Hyperloop competition. Now, since that day, we've expanded our team from an idea into a reality, and we have reoriented our goals to focus on improving the Hyperloop community here in Canada. We are proud of the progress we've made to this day, and we'll be demonstrating some of that to you. I will start by handing us off to our project lead, JP, who will be starting the conversation on our software system. Over to you, JP.
All right, thanks, Bruce. So I'm going to start by talking about OpenLink. OpenLink is our design for a modular open source software system to solve a lot of the problems that we've identified that a lot of Hyperloop projects face across Canada, in the US, in the entire world. So we're trying to attempt to solve some of these problems with OpenLink here. So let's go over a few of those problems that we've identified. The first one is scalability. A lot of the systems that we've identified so far are created ad hocly. As a result, adding additional electrical systems, additional electromechanical systems to your pod is extremely complex, and it introduces more errors to the process. So it lacks that inherent scalability, which is what we're looking for in software. The next is unpredictability. When you have software that's created ad hocly and you don't have any systematic procedures in creating it and adding and removing electromechanical devices, there's a high risk that there could be race conditions, that there could be issues, different resources trying to access different resources at the same time. There's a lot of things that could go wrong, and we want to avoid those problems as much as possible. The final problem that we identified was inconsistency. We noticed that amongst the Hyperloop community, there's a huge array of different software solutions available. As a result, it made it really difficult trying to collaborate with other teams and trying to help other teams with their software system, trying to get help from other software teams. It makes collaboration a lot more difficult. So we're hoping to propose kind of a new grammar and a new way of looking at software systems to address some of these problems here. So the conclusion from this is that ad hoc software in an alternative transportation system such as Hyperloop is extremely dangerous. We don't want to be creating software that is going to be linking systems together that has the chance, if they fail, to risk human life. We want to avoid this as much as possible. We want a systematic approach to this. So the goals of our software is to achieve scalability. We want any team to be able to add as many electromechanical systems as possible to their Hyperloop pod. It should be predictable. So we should be avoiding race conditions, as well as there should be a suite of test cases that we can use in order to predict how well your electromechanical systems are going to perform in conjunction with your software. And finally, it should be standardized in some sense. We should have some standard protocols that we use and some standard grammar that we use when we're talking about software in Hyperloop. So I'm going to pass it off to the software lead, Matthew Holden, who's going to talk about our proposed solution in a little bit more detail.
All right. So this is a high-level overview of our software system that helps show how we meet all of our goals. For predictability, we have 3 subsystems that have clear-cut boundaries and roles. This also leads to clear-cut channels of communication to meet our standardized goal, making it easy to identify points of failure and make redundant countermeasures. The use of Ethernet inside the pod meets our scalability goal, as adding new subsystems is simplified. For the languages we'll be using, we really wanted to leverage and use Rust wherever we could. On the embedded side, we've identified a couple microcontrollers that we can compile Rust to that we'll be using for our sensor subsystems and possibly others. For any remaining microcontroller that doesn't support Rust, we'll obviously be forced to use C. The pod computer and remote client will also be written in Rust. For network libraries, we'll be using Quiche to implement the Quick protocol in the embedded system, the pod computer, and the remote client. This is a library written in Rust, so for embedded devices that can't support it, we'll be using Pico Quick. For async, we'll be using Tokyo in the embedded system, the pod computer, and the remote client. Again, this is a library written in Rust, so for embedded devices that can't support it, we'll be using libevent. For the remote client, we were targeting WebAssembly right in the web browser, but unfortunately the system interface to open up UDP sockets we need for Quick is just too immature at this point. So we've decided to use Tari, which is basically a really efficient alternative to Electron written in Rust. That way we can still use WebAssembly as our front end, but have that lower level access to the system. We'll be using a Rust-based WebAssembly framework called U as our front end. Also not shown would be how we're storing our data, both on the pod computer and remote client. We'll be using an embedded NoSQL database called unqlite. So here's our use case diagram representing the different user groups we've identified for OpenLink and the various ways they interact with our system. These software team members will be responsible for things like configuring the pod subsystems and exporting data. The mission control team members will be responsible for controlling and monitoring the pod. The administrator will be responsible for things like account management. The pod computer will also play a role in the operation of our software, as there's a watchdog service to monitor all telemetry data and automatically initiate an emergency stop if unsafe conditions are detected. So this is our class diagram for the pod components, our pod computer components. The pod connectivity service manages all outgoing and incoming packets in the pod. Through that, we can utilize the functional services for starting and stopping the pod with the launch and brake service, reporting telemetry for each subsystem with the telemetry service, and adding and removing subsystems with the link service. The emergency service monitors all telemetry data and initiates stopping the pod if an unsafe condition has been met. Telemetry data is also stored with the database service to function as sort of a black box. The remote client connects with the remote connectivity service and utilizes the authorization service to access specific pod functions. Again, so this is the class diagram for the client components. Again, the remote client utilizes the remote connectivity service to interface with the pod. Pod functionality would be operated through the API service. Telemetry reported with the data service and stored client side with the database service, and permissions are restricted through the auth service. I'm going to pass it off to Yamini to start the Flywheel portion of our presentation.
Thank you, Matt. I'll be giving an overview of our Flywheel design and how we came up with the concept today. So in order to best design and adapt our pod, we need a testing space, and it requires a location that we can build a minimum of 100 meters of length in test track. Having a longer track just means that we have more realistic testing conditions, but unfortunately, there just aren't the current facilities built near us with the applicable space and testing requirements. For feasibility, a track must be reusable and adaptable. It must be able to work within a variety of conditions, but a major concern comes with the open air track because it cannot be used during certain weather conditions. It would need to be removed and later replaced, which would be expensive and time consuming and could often be considered a waste of resources. There would also be a slew of safety concerns and considerations that we'd have to take into effect at that point. Our main solution was building a Flywheel. This is a Hyperloop testing system that can be used indoors, and it's easy to use, safe, and simply calibrated in order to test for the safety. There's no need for weather applicable maintenance, and it's usable year round, and it also gives us unlimited test track to test on. can be reused and replaced over the longevity of our project when we use different propulsion systems with our electrical and mechanical subsystems. And it's also adaptable because we can modify and change the parts that we test using this flywheel with the application of new innovative technology. Our problem parameters were that we wanted to use a similar design to the water loop test track, which the CHC competition would be using. This includes the material, the thickness, and even heat management systems. And we'd be able to use that in order to obtain test data. It can be modified, especially with the use of the new electrical and braking subsystems that we'd want to test on here. For safety, it also requires proper management of an enclosure, including proper barriers and safety stops. And we'd also want to reduce the potential errors and failure modes that would come with this. This includes managing cooling systems to prevent overheating of the subsystems and also to protect our team. And also requires the creation of an operations manual with safety procedures that would require all the users to be trained in the testing and usage of the flywheel. Now we'll hand it off to Matt to give an overview of our safety considerations for the flywheel.
So one of the most important considerations when it came to our flywheel design was safety. So one of our first steps was actually creating a general operating procedure to ensure that all operators use this device in a safe manner. This procedure included things like guidelines for starting and stopping the device, data collection, and emergency situations, while also ensuring that all users are aware of some of the general warnings and hazards that might be associated with using the flywheel. So in addition to ensuring that the flywheel is being operated safely, we need to ensure that the design itself is safe. So to this effect, one of our first steps was actually performing a stress analysis to ensure that the flywheel was safe to operate at the expected speeds. So as you can see here, we actually evaluated different wheel speeds and different wheel diameters, and we were able to determine that we're able to run safely up to about 1,000 kilometers an hour, and this is with a factor of safety of 1.5. Off to Amit to discuss the current state of our flywheel design.
Thank you, Matt. So as you guys can see, this is a 3D model of our final flywheel design. It was done via SolidWorks. As previously mentioned by Yamini, the team wanted to test the linear induction motor assuming an unlimited track length, and we decided that using a flywheel would meet that demand, as the linear induction motor could prolong its active duration, and therefore Trillium Hyperloop would be able to fully exploit the capabilities of a linear induction motor. The schematic is set up to be removable and adaptable. Therefore, different variations of propulsion systems and braking paths can be tested. The material to be used is the aluminum alloy 6061, which is the same as the testing track. As also mentioned, the entire schematic will be an enclosed cubic container, mostly made out of reinforcing steel bars and strong glass for transparency and protection. The top of the container, however, will be open to ambient air, and this is done for cooling purposes. The piston tube-like feature in the back are essentially hydraulic pistons, and they serve as a dampener in order to minimize vibrations. As a future consideration, Trillium Hyperloop will be looking into different types of bearing designs for the flywheel. Therefore, this schematic will be the final schematic that will serve Trillium Hyperloop as a basis for experimental data for years to come. Next. So as we all know, thermal analysis is a very vital step into completing a detailed design and ensuring the adequate factor of safety requirements are met. As seen in the schematic in the previous slide, the linear induction motor is placed at approximately 50% of the outer radius and is at a 2 millimeter distance from the flywheel. Therefore, it is very susceptible to thermal loads. Therefore, to ensure that there is no risk to damaging the linear induction motor, a thorough heat transfer analysis was conducted. The first step was to calculate the overall heat generated through braking, and this was done through first considering the conservation momentum equations through the 2 G's of braking force applied. And from there, we're able to calculate the overall time required to bring the flywheel to a full complete stop. Using the time, we were able to use the conservation of energy and transferring the kinetic energy into heat. The overall thermal load was 9.38 megajoules of energy, which is a lot of energy. So given that, we went to calculate the final temperature of the flywheel, which came up 630 degrees Celsius. We did so by considering all forms of heat transfer, including convection and conduction, and also radiation. Given that we have the final temperature of the flywheel, it's now important to ensure that the linear induction motor does not exceed its maximum operating temperature. And doing so, using the heat transfer radiation from the flywheel to the linear induction motor, and also considering the shape factors, we were able to calculate a full thermal load of 109.44 kilojoules for the entire time lapse of the flywheel's rotation, which then comes up to a final temperature of 32.6 degrees to the linear induction motor, which is way below the maximum operating temperature of the linear induction motor, and therefore this serves as a optimal factor of safety operation. I'll now pass it on to JP for the closing comments.
Thanks, Ahmed. I just first of all want to thank the organizers for CHC for hosting this wonderful event. I had the opportunity to view so many wonderful teams give presentations, and it's extremely encouraging. Everyone on our team is absolutely committed to making Hyperloop a feasible technology of the future, hence the emphasis of our two designs that we presented today. First was OpenLink, which is our attempt to kind of make an open sourced, iterative-based software solution for the Hyperloop community. And we could start talking more seriously how we're going to talk about implementing software systems and implementing complex scheduling conflicts for Hyperloop pods in the future. These are very important problems that we have to solve. Second of all is the flywheel. We want to enable teams to test their linear induction motors and test their things anywhere, no matter what. So we're committed to making everything that we do completely open source and completely up for discussion and communication with the Hyperloop community. So on that note, if any of you have any questions in regards to OpenLink, you can contact me personally. I'm available on every single form of social media, although I did delete Instagram recently because exams are coming up. You can also contact Matthew Holden as well, who's the software team lead. In regards to the flywheel, you could contact Yemeni, the chassis team lead, Ahmed, the aerobody team lead, Matthew Collier, the braking team lead, or Bruce, the limb lead. Please contact us. We're really eager about talking with you guys about this stuff, and we want to help the community as much as we possibly can. So in regards to contact information, here's all of our contact emails. So if you guys have any questions, you could shoot us an email. You could also visit our website and contact us through there, or you can connect with us on LinkedIn. So that's it for our presentation. If anyone has any questions, you're more than welcome to ask us.
Thanks for your presentation, guys. Yeah, if anybody has any questions, feel free to ask.
Hey, I had a question about OpenLink. Do you guys have like a rough timeline for when you'll release something?
Yes. We're working on 3 sprints right now. So we're due to finish the first sprint December 9th. So that should have the basic functionality. We're going to be connecting the GUI with the back end for the pod computer. And so we should have that done by the first sprint, and that will be up on our GitHub. And in terms of the second and third sprints, we'll be done the second sprint end of January, early February, and the final sprint will be done early spring. And then we'll have a fully completed version, all available on our GitHub for everyone to look at.
That's awesome. Yeah, it looks like a really cool system.
Thank you.
Any other questions, anybody?
Actually, just as a follow-up question, but would you see this being able to be used for other types of battery electric vehicles as well, like electric bikes or things like that?
Yeah, for the software system?
Yeah, for OpenLink.
Yeah, for OpenLink. I think it could probably be cross-applicable. The main goal, so we would just have to have like some form of operating system. Like you could have like a micro OS on like on like a bike or something, and you could control that. The reason why we chose Rust was because we wanted to integrate in the future with WebAssembly. You know, WebAssembly is going to be like an amazing feature where you could run native applications on the internet. So that will we think that's probably going to democratize a lot of the computational effort that's needed for for CPU calculations, things like that. So it would make it very advantageous for something such as like electric vehicles or for even electric bikes. Who knows, maybe they could even outsource some of their computational complexity to WebAssembly, which is why we decided to go with WebAssembly for the implementation of OpenLink. because we expect sometime in the future, by the time Hyperloop rolls around, we'll probably have WebAssembly. They're already rolling out the first iteration of that. So by the time Hyperloop becomes a feasible form of transportation, we expect that WebAssembly will be an integral part of controlling the scheduling of Hyperloop systems, because it's so good at handling race conditions that it would be optimal for that. So does that kind of answer your question?
I think so. Yeah, I'm not super well versed in software, but I think
okay,
that clarifies some things. Yeah, thanks.
Yeah, and feel free to shoot me an email or hold in an email if you have any more questions, and we'd be happy to answer them.
Cool. Yeah, thanks, JP.
Yeah, no worries, man. Any other questions about the flywheel? I guess we explained it well.
I have a quick question about the flywheel.
Yeah.
So which material do you guys plan on building it out of? And like, did you have to plan that based on the, like, obviously it's reaching extremely high temperatures, so is it like a pretty specific type of material?
Ahmed, Yamini, Matt, you guys want to comment on?
I guess I could take this if it's related to heat. Yeah, so we have to use the same material as a track, because we have to model the flywheel conditions exactly like how the linear induction motor will operate on the track. However, given the fact that the flywheel is moving at almost 1,000 kilometers an hour, there is a lot of convection heat transfer occurring, which removes a lot of heat from the actual flywheel itself. And the maximum operating temperature of the aluminum alloy specifically is pretty high, somewhere around 750 degrees Celsius. So it won't be a concern, given the fact that we have a lot of convection occurring and also conduction through the diameter of the flywheel. So it should be fine.
We'd also be considering using a cooling system using pressurized air within the box or the enclosure for that flywheel. So we're trying to decrease the effects of heat occurring that would affect the linear induction motor and the braking.
Right. Okay, that makes sense.
I think there's a question on the chat, by the way.
Yeah, just a question in the chat. You mentioned that you were using Ethernet cables. What sort of RF shielding, if any, do you plan to use?
So I'm trying to find that in our documentation, but we will be using I forget what they're called. It's kind of expensive to do it with like medical grade stuff, so we're just going to use some simple I can't find it, sorry.
Question from Emrys.
I just had a question about the flywheel as well. So I think you mentioned that you're using some actuators for damping. Is that right? How does that work?
So this design was proposed by one of the professors at our faculty of engineering. This exact design is actually implemented at Western University for a different application. We were like advised to use this kind of form of actuation, like you mentioned. It's basically to dampen the vertical oscillations that could occur. Now, given the fact that the flywheel is geometrically proportionate, there should be no sort of forcing factor to kind of force it to vibrate in a sense. But just in case that happens, the hydraulic pistons kind of have a really high stiffness, enabling it to kind of counteract any form of oscillations. So does that answer your question?
Yeah, kind of. I'm curious about how, is there like one end of the actuator that's fixed to the center of the flywheel, and then the other end is fixed to the mount? Is that how it works?
Yamini, would you be able to add more into this?
Sure. So are you talking about like those moving pistons themselves?
Yeah.
Like in the image? Okay, yeah. So one end of them is bolted onto the center of the flywheel. So as you can see in this first image on the left, one end of it is connected and the second end is kind of moving within a shaft up and down as the wheel spins. And that helps with damping. Since there are less like moving parts that are touching each other, it also helps with the cooling within that area. But yeah, it's mainly used for damping of the system.
Okay.
Yeah, it's not like spring loaded or anything. It's just moving vertically within that shaft as the flywheel turns.
Okay. Cool. Thanks.
Any more questions from anybody?
Holden, were you able to find the answer to that guy's question?
No. Still searching,
Right.
sorry.
All right. Well, just shoot Holden an email, and we'll get back to you on that. Apologize, we don't have the answer off the top of the head right now, but it's in our documentation, and we'll get that for you.
Alrighty, well, if there's no more questions, thank you so much for your presentation. That was really great, really informative. And now I'm going to pass it off to Daphne and Christina